In single variable calculus, you learn that the function f of x equals e to the x is the only function whose derivative equals itself. Now that function is called the exponential function. Well, what we'll find today is that matrices have an analogous concept called matrix exponentials. So let's jump in with a motivating example. What you're looking at here is a cascade of saltwater tanks. So the way that I want you to think of this diagram is I want you to think of these two tanks. One has volume 20 liters and the other has volume 40 liters. I want you to think of these as full of salt water. And when I say this is a cascade, what I want you to think of is that there is liquid being pumped into the first tank, and then liquid in the first tank is then being mixed and pumped into the second tank, and then liquid in the second tank is being mixed and then pumped, and liquid is pumped out. Okay, so these are tanks of salt water. In the first tank, the initial salt content is 10 kilograms, and in the second tank, the initial salt content is 30 kilograms. So let's take a closer look at the precise situation here. So we have our two tanks, and pure water is being pumped into the first tank at a rate of 10 liters per second. So that's represented in our diagram here with this squiggly arrow. There's pure water being pumped into the first tank at a rate of 10 liters per second. Now remember that the content in the first tank is salt water. So there's pure water being pumped into a solution of salt water. Now the content in the first tank will be mixed, and then whatever that mixture is, it will be pumped out into the second tank at a rate of 10 liters per second. So there's liquid being pumped into the first tank, and there's liquid being pumped out. The rates at which that liquid is being pumped in and out is the same. So the volume in the first tank is remaining the same. But the idea is that we have an initial salt content in the tank, and we're sort of flushing the salt out by pumping in fresh water and then pumping out the solution. Now that solution gets pumped into the second tank where the initial salt content is 30 kilograms. So the content in tank 2 is mixed and then pumped out at the same rate, 10 liters per second. So we have fresh water sort of flowing into this system of salt water in both tanks, and then the mixture in both tanks gets mixed and then pumped out into the void. So the question here is that given this setup, how much salt is in each tank at a given time t? So that's our general setup here. So at first glance, this sort of looks like some sort of calculus problem because we're talking about rates at which things are changing. So then the question is, well, how might we set this calculus problem up? And a good way to approach this is to think of what's called the chemical balance law. So the chemical balance law is a principle in chemistry which says that the rate of change is equal to the input rate minus the output rate. So how does this sort of play into our situation here? Well, let's introduce functions to help keep track of the amount of salt in each tank. So let's let u sub I of t be the mass of salt in the ith tank at any given time. So u sub 1 tells me the mass of salt in the first tank, and u sub 2 tells me the mass of salt in the second tank at any moment in time. So if we think about our situation here, what we're doing is we're modeling the rate at which the function u1 and the function u2 is changing over time. So remember, there's fresh water being pumped into the first tank. That solution is then mixed, and then that solution is pumped out at the same rate. So if we pay attention to the derivative of u1 here, we can separate out the input rate and the output rate as far as the mass of salt is concerned. So let's take a look at the input rate of salt. Now, because this is fresh water, we know that the input rate is 0, but I want to pay attention to the units here. So the the rate at which fresh water is being pumped in is 10 liters per second. So that's the velocity of fluid flow into the first tank. But if I think about it, since that's fresh water, that means that the salt content is 0 kilograms of salt per liter. So the first derivative u1, if I think about the input rate here, it's 0, but the right way to think about 0 here is as 0 kilograms of salt per liter multiplied by 10 liters per second. Now let's think about the rate at which salt is exiting the tank. Well, here we have our mixed solution, and it's being pumped out at a velocity of 10 liters per second. So now I'm subtracting the rate at which mass of salt is leaving the tank. The velocity is 10 liters per second, but what's the concentration here? The concentration is whatever the amount of salt is in the first tank, that's called U1, and we want this per volume, so this is U1 kilograms of salt per liter, which would be divided by 20 liters. That's the volume of the first tank. And when I simplify my arithmetic here, this simplifies to just negative 1/2 U1. So I have my first differential equation here. The derivative of U1 equals negative 1/2 times U1. Let's now look at the second tank. The second tank is a bit more complicated because we have a mixture of salt solution being pumped into the tank, and then that mixture is mixed, and then our salt solution in the second tank is being pumped out. If we apply the chemical balance law, we can think about the rate at which the content of salt is changing by looking at the input rate and the output rate. So what is being pumped into the second tank? Well, that's the mixture from tank 1. And in the mixture from tank 1, we know that the velocity is 10 liters per second, but the concentration of salt in that liquid is whatever the amount of salt is in the first tank at any moment in time. That's U1 kilograms of salt per liter, so then we divide by the total volume of the tank, which is 20 liters. When we simplify this, this just ends up equaling 1/2 times U1. Now let's take into account the amount of salt exiting the tank over time. So what is leaving the second tank? Well, the velocity at which liquid is leaving the tank is 10 liters per second. But what is the concentration of salt in that escaped liquid? Well, this would be the amount of salt in the second tank, that's U2, divided by the volume of the tank, which is 40 liters. So we have an input rate and an output rate here. For the first tank, the input rate of salt is 0 because there is fresh water flowing into the tank, but the output rate ends up being negative 1/2 times U1. For the second tank, there is an input rate of salt, which is influenced by the amount of salt in the first tank. That input rate ends up being 1/2 times the mass of salt in the first tank, U1. But then we have to take into account what is exiting the second tank. And when we simplify here, that's minus 1/4 times U2. So in this situation, we are now looking at two equations that are related to each other. The derivative of the first function, U1, is equal to negative 1/2 times U1. But the derivative of the second function, U2, is equal to 1/2 U1 minus 1/4 U2. This is what we call a linear system of ordinary differential equations. So we use the abbreviation here, ODE. Now, we would like to be able to solve this system of equations, and we've been solving systems of equations in this course, but the systems of equations we've been studying have really nothing to do with calculus up until now. So let's take a closer look at our situation. Our situation can be distilled down to these two statements here. Or these four equations, if you want to think of it this way. The derivative of U1 is equal to negative 1/2 U1. And the initial value of U1, that's the initial amount of salt in the first tank at time t equals 0. That was equal to 10. The derivative of U2 was 1/2 U1 minus 1/4 U2. And the initial amount of salt in the second tank was equal to 30. So the first thing that I want to point out is that we can use matrices to better encapsulate the data of this system. So how does that work? Let's define a vector, u of t, that organizes the data of u1 and u2 in two different coordinates. By introducing this vector, we allow ourselves to use the language of matrices and vectors to represent this system. So what am I looking at here? At the very left, I have a vector, u1 prime, u2 prime. That's organizing the data at the far left of the system of equations that we started with up here. And if we think about it, this would be the derivative of the vector u. And by derivative here, I mean we go coordinate by coordinate and take derivatives. What about the second part in my system? Well, what I'm looking at are coefficients in front of u1 and u2. This is something we've seen before. The way to think of this is as the coefficient matrix. The rows here would be -1/2 and 0, and then 1/2 and -1/4, multiplied by the vector organizing u1 and u2. That's the vector bold u here, u1, u2. I also have these initial values to account for. The initial values are u1 of 0 equals 10, and u2 of 0 equals 30. That can be viewed as one vector equation. On the left here, maybe I can call this bold u of 0. So that would be what I would get if I plugged in t equals 0 into my vector function u. And this is equal to some constant vector, 10, 30. The notation we'll use here is bold u subscript 0. So that's the initial value of the vector u. So what we've done here is we've taken the data from our take problem and represented it as a vector differential equation. This is vector u prime equals a times vector u, where the initial value of the vector u is equal to this constant vector u sub 0, which is the vector 10, 30. So the question then is, well, how do we solve this? So hopefully we see now how we can set this problem up, but it is not so clear how we could be able to solve this system. So in order to get a good idea here, I want us to remind ourselves how this sort of problem would have worked in single variable calculus. So instead of having two functions that we're trying to manipulate, let's just imagine that we had one. If we had one, the problem would look something like this. So this is a famous initial value problem, and this is the initial value problem where we have a function y whose derivative is a constant multiple k of itself. And maybe we have an initial value for y, that would be y of 0 equals some constant y sub 0. And the idea is that in single variable calculus we learn that this initial value problem is uniquely solved by one function, and that function is y sub 0 times e to the kt. So if I take a derivative of this equation, I would get y sub 0 times e to the kt, and then with the chain rule, I would get a constant multiple k. That's equal to k times y0 e to the kt. Furthermore, if I plug in t equals 0 into this equation, I get y naught times e to the 0, which is 1, which equals y naught. So in single variable calculus, we know how to solve this problem, and the solution involves working with the exponential function, e to the t. So maybe a question we could ask then is, can exponentials help us solve the problem that we are trying to study? If we have a system that's represented as u prime equals a times u, much like in a single variable calculus where we have y prime equals k times y, perhaps we can take advantage of the idea of exponentials to help us solve this problem. So that's the setup here.